Okay, so before we get started today, there will be a meeting with me, Shoaib, and the student representatives. So if you have any feedback, you have a little bit of time before the meeting, so we meet straight after the lecture. But otherwise, the technical content of today's lecture is to talk a little bit about Ethernet as being one of the most popular LAN protocols that we have, and then talk a little bit on how to connect different LANs together with hubs and switches. In particular, we will talk about something called transparent switches, and for these to work, there is something called the spanning tree protocol that we will discuss here a little bit at least. But if we look at LANs, local area networks, so we talked about this earlier in the course, but what can we say about this though we refresh our minds? So a local area network, what is it? Well, it's something that typically is physically rather small, so distances maybe less than a kilometer or so from end to end. And typically, at least in the beginning, it was used over a broadcast medium, which means that we need a medium access control scheme for this. Hosts attached to this network. Remember, host is like an end user, end equipment somehow, a laptop, cell phone, or something like that. Something which is at the edge that connects to the network. Right? So these are moved around. So, for instance, if you think Wi-Fi is a LAN protocol, so obviously we move around, right? Each network interface card, which is the gadget that attaches to the network, or this is sometimes called a NIC also, is given a unique physical address, MAC address, also known as a MAC address. So physical or MAC address is the same. And this is something that is fixed for the network interface card for all times, at least in theory. And these are also unique on a global scale, at least in theory. Now, in practice, one can software change the MAC address of your network interface card if you like. So, but the idea is, at least, let's pretend that they are globally unique addresses. Transmission then over a wired medium. If we have a wired LAN, typically these are not so affected by errors. So, no sophisticated error control techniques are required typically for these type of connections. However, if we do that over wireless, then it's a completely different matter. Here, there will be a significant amount of errors sometimes, and we need to have mechanism to handle this. And LAN protocols are placed in the link layer. All right, so that a little bit of a refresher. So let's go in and talk about some practical protocols here. And if you remember the OSI stack, we have the lowest layer is the physical layer, and then there is the data link layer. And then on top of that is the network layer and so forth. But we are concentrating now our discussion on the data link layer in the OSI model. So practical protocols which are used in practice here are determined by either by companies or by standard organizations and so forth. So there is a standardization organization called the IEEE. So it's I and EEE, that's how you pronounce this. It's the Institute of Electronic and Electrical Engineers, I believe. And they have a committee or some type of entity called 802. And they do these type of standards. Okay, so the 802 family of standards, there is something called 802.2, which is also known as the Logical Link Control, or LLC. This forms the upper layer of the data link layer in the OSI model, and below this there is a number of medium access control schemes, MAC schemes, in the IEEE nomenclature. We have the link layer control and the MAC layers. So there are many MAC layers below this logical link control layer. So this one, everything that goes in 802 goes over this one, with some exceptions as we will see later on. So what kind of MAC layers do we have? Well, we have an 802.3, which is CSMA CD, and this is also known as Ethernet. There is Wi-Fi, there is something called token ring, and there is a bunch of others. I would say that these two are the most common ones. And below each of these, there are various physical layers. So not all Macs can use all physical layers, but one single Mac, for instance, Wi-Fi, have many different physical layers you can choose from. Not all of them are implemented, but they are in the standard. Okay, and they are too many to mention here, I would say. Okay, so if we talk about services, these Macs, they provide a service. So they provide a service to the LLC layer, and they provide an unreliable datagram service. So basically, they accept packets and send them. That's it. They don't try necessarily to correct anything, or at least they don't provide any guarantees. So the link layer control enhance this service. So the service which goes up here is enhanced to the service that goes up to the upper layer here, to the network layer. And there are three types of services: type 1, type 2, type 3. Type 1 is the most used one, and that basically does nothing. So it just basically provides unacknowledged connectionless service of packets. So packets go down here and LLC guarantee nothing. Right? There are also type 2 and type 3 possibilities here, where type 2 is a reliable connection-oriented service. This is optional. And an acknowledged connectionless service, this is optional. So this one, type 3, basically sends if you go send a packet down, you will get an acknowledgement back when it's delivered. Okay. Type 2 is when you have a stream of packets here, and then you can guarantee delivery of packets in order. So there you need some type of ARQ protocol. We will not talk about 2 and 3, but just talk about 1 here. And LLC supports multiplexing on many network layer protocols on top of this. So there could be many protocols on top of LLC at the same time. Okay, any questions so far? No. Okay. So let's look a little bit about the protocol data unit structures here. Now, so these details, are they important? Well, in a way they're important because they illustrate how a practical protocol used the generic stuff that we have talked about. Now, at the exam, I will probably not ask you how many bytes are there in the SAP address of an LLC PDU, right? So those type of details are not super important, but the general structure of PDUs is important, and this we have talked about many times. Is some type of overhead, and then there is some service data unit, which is the payload that we get from the layer above. Those type of structures are important. Number of bytes in each field is not super important. Okay, so but the link layer PDU consists then of some data that the link layer has gotten from above, and then there is some control information here. There's a destination address, a source address, a control byte here. And then in certain circumstances, one extends this header to 5 more bytes here. So we'll talk about that shortly, what that means. Okay, this whole PDU, the LLC PDU, is then encapsulated in the MAC PDU. So the MAC PDU consists of a MAC header and then the link layer control PDU, which is what's above here, and then a frame checksum on the whole thing. Okay, so this is typically a CRC. Okay. So these SAP addresses, service access point, if you remember that acronym. So SAP service access point. The destination SAP address that identifies the upper layer at the receiver. Okay, the source SAP address identifies the upper layer at the source. So whatever upper layer we have here, has this data, and it's some type of layer. Say it's IP, for instance. Then the source would then identify IP in this case. And then the destination is most likely IP also. Right? But it could be different, right? So for different upper layer protocols, of course we have different types of data here, but that's not should not be used by the LLC, but we use the source and destination here to figure out what the upper layers are. Okay, so there is one protocol, for instance, called the Bridge Spanning Tree Protocol, and we will talk more about that later on. It's identified by the byte 42. So this is in hexadecimal. So 4 is the first 4 bits, and 2 is the second 4 bits. There is a special SAP address called AA, and that identifies something called SNAP, or Subnet Network Access Protocol. Okay, and this, if it says AA in these fields, it means that we should interpret these bytes as control bytes, not data bytes. And these control bytes then allows multiplexing protocols that don't have their own SAP addresses. Because since we have 1 byte here, there are 256 protocols that we can address with this. This turned out to not be enough, believe it or not. So in cases where you would like to support other protocols, you do that by using SNAP instead, and then you use this extension to identify the upper layer protocol. Okay. Again, a little bit of details here, right? But I mean, practical protocols are not as clean as we presented protocols earlier, because they have to, take care of many practical issues. And they also evolve over time, which means that sometimes they're patched in an ugly way. Okay. Any questions so far? All right. So then let's go into Ethernet. And Ethernet is the dominating wired LAN standard that we have today. And so it might be interesting to know a little bit about the history of it. Remember that we talked about ALOA a couple of lectures ago. So this in the 70s, this ALOA is actually a practical radio network that was deployed in the Hawaiian Islands, and we used this medium access control scheme called ALOA. Then in 73, 2 persons, Metcalf and Boggs, basically took these main ideas about ALOA and put that on a wire instead. So they invented this early form of Ethernet, which is random access in a wired net. Basically this is the sketch of it that Metcalf has. So one has here the yellow thing here is a coaxial cable, which has terminations at the end here to make sure that signals don't go back and forth and bounce in this, right? So we have some termination here. And then if one wants to share this coaxial cable between different computers, basically one drill a small hole here and put in a plug here called a tap. And then there is an interface cable to the actual computer where there is some interface card, a controller, whatever, and here we have the computer. Okay, and when we want to add another computer to this LAN, we basically drill another hole in this coaxial cable and input another tap here and so forth. So then all these hosts then compete for access on this cable. And he called the cable the ether. The ether is this mythical idea about how radio waves propagates in space, right? Basically he called that this Ethernet, right? And then this was called Ethernet 1, or it was called Ethernet, but at a couple of years later, 6 years later, there was an Ethernet 2 standard that was developed from these ideas. And in 1985, the companies that were behind this Ethernet standard handed over the standardization responsibility to the IEEE, who then did the first Ethernet standard in the IEEE family, and that's called 802.3. It was a 10 megabits per second standard. And then in 95, there's a 100 megabit standard. In 98 was gigabit standard. 2002, 10 gigabits. 2010, 40 and 100 gigabits standards, right? So it's been developing, and you see as the development is perhaps a little bit faster at the end here. So today, Ethernet is the dominating LAN standard. Okay. So let's talk a little bit about then 802.3 medium access control. So what is it? The medium access control is based on CSMA, CD, collision detection. So what do? We sense the channel. If it's idle, we transmit. If it's busy, we sense until free and then transmit. So this is one persistent CSMA. So basically, if we have time here and the channel is busy when we want to transmit, we wait. We continuously wait until this time, and then we put, there will be like a nanosecond, and then we put out our frame here. Okay. Now, this was a successful thing, but if there is a, say then that another terminal station would like to transmit here, it senses here, and then sends its frame here, but perhaps there is also a green user would like to do it like this, and then the green frame would be transmitted basically at the same time. These will be detected as collisions, and then we go into back off. Like this. So CSMA with one persistence. CSMA with collision detection, basically as we talked about earlier in the course. When collisions are detected during transmission, one aborts then the ongoing transmission. So we cut these colliding frames short, and then back off a random time of mini-slots time, and then start over. So the critical system parameter here is this mini-slot time, or T-slot, and it has to be greater than 2 times the propagation time for this to work. We'll see on the next slide why this is the case. So the mini-slot time is then roughly the duration of these contention periods. This is a contention period, and therefore also equal to the minimum frame duration. You'll see that on the next slide. So anyways, when there was a 10 megabit standard, one thought, okay, the maximum cable length would be 2.5 kilometers, so it's fairly big LAN, right? But think of it like this: as soon as you draw a cable, you have to draw it in the walls or whatever. So even though that the straight line between two computers might be 100 meters, then the cable length might be substantially longer than this, right? So anyways, there was a thought that, okay, maximum cable length of 2.5 kilometers, and for the signal to not be attenuated too much, one put in 4 repeaters, basically amplifiers in this. The amplifiers also take some time to go from input of the amplifier to output of the amplifier. One did a few rough calculations and came to the conclusion, okay, from end to end, in worst case, it will take you 50 microseconds. Okay, once we know 50 microseconds, then we choose what the minimum frame length has to be, and it was chosen to be 64 bytes, which corresponds to 51.2 microseconds. Because here, 1 bit equals 1 over 10 megabits, so 10 to the power 6. So this is 10 to the minus 7, which is 0.1 microseconds. So that's how you calculate the correspondence between bytes and seconds, right? Okay, 64 bytes is 64 times 8. So what is that? 128 to 56, 512 bits. Okay, 512 times 0.1 microseconds, 51.2 microseconds. Okay, All right, so this minimum frame size and so forth, what does that come from? Well, it comes from that we want to be able to, we want to be able to detect all collisions. Okay, and then if A starts to transmit at this time, when is the first time it can notice a collision? Well, the first time it can notice the collision is the time it takes to go to the other end, and then the frame from the other end can start at this point without violating the sensing. Station C here will sense the channel to be idle until this time. So this is the last time Station C can start to transmit. And if it does that, then this is the latest time when Station A is aware of that transmission. So it takes 2 t-prop from A to notice that there is another collision on the channel, in the worst case. Could be smaller than this, but this is the worst case. So after 2 t-prop, 2 things can happen. Either you know you have the channel, that you're the only one on the channel, or you have detected a collision. Okay. So we talked about this earlier, right? But just to refresh your minds. So in Ethernet then, one decided, okay, the minimum frame length has to be 64 bytes, which corresponds to 51.2 microseconds. And this is for 10 megabits per second. Okay. Then this backoff is also binary exponential backoff that we talked about earlier. The only difference is that it's truncated. So to refresh your minds, what is binary exponential backoff? It means that the backoff time is random every time we back off, and it's R, a random number, times t-slot. So t-slot is our time unit. So how do we choose R? R is chosen randomly in an interval from 0 up to 2 to the power of k minus 1. So how do we know? How do we calculate k? Well, something like this. So we choose R randomly in the interval from 0, 1 up to 2 to the power of k minus 1. So small k here. So small k is calculated from capital K, where capital K is the retransmission count. Okay, so either we have our first retransmission, our second retransmission attempt, or the third time we go into back off, so forth, right? So we continue here up to 10. And then we have 11 up to 16 is the last time we try to transmit the frame before we give up. Okay. And then to find small k from large k, then k is the minimum of capital K and 10. So what does that mean? Well, it means that when we try the 10th event, we saturate small k to 10. So for 11 it's 10, and up to 16 it's 10. And from 0 to 10 it's a linear increase. So it's 1, 2, etc. like this. So this is the way we increase small k as a function of large k. And we see that the increase in the maximum backoff time, or maximum R, if we look at the maximum value of R, how that progresses as we increase k, then for capital K equals 1, small k is also equal to 1, and the maximum value is, the maximum value is 1. 2 to 1, 2 to the power of 1 is 2, minus 1 is 1. Okay. The next attempt, it will be 3. Next attempt, it will be 7. And then we continue like this until we hit 10. And then it will be 2 to the power of 10 minus 1, which is 1023. Okay, and then it will be 10, 23, all the way to retransmission event 16. After 16, we just give up. So we see here that there is an exponential increase in the maximum value of R. Questions? Okay. So then, if one looks at how the channel looks during when we have many, so if one would just look at the channel how it looks, then at some point there might be a frame being transmitted like this, and then the channel would be busy, right? Then every other station that would like to transmit the frame and start to sense the channel during this time will then wait until the channel becomes available. Okay. If there are more than one that's waiting here, then all of them would start to transmit at the same time, and then we would get a collision here. Right? It would take a little bit of time to detect that the channel is available, and once it's available, then all nodes will go in and start to transmit. Okay, and if there is a collision, then the transmitting stations goes into back off, right? So they will back off according to this, and in the first event, they can choose from back off 0 or 1. So some of them will choose 0, which means that they don't back off, and then they will try again and fail, right? So there might be another collision. And then those will go into back off also, and now the selection is between 0, 1, 2, up to 3 for the second retransmission events. So now there is a bigger chance that we spread these out so there won't be a collision. But suppose that there is a collision anyways, right? Then it will look something like this, and then we go into retransmission event number 3, and then it's from 0 to 7 that we can choose from. And maybe now it resolves itself, so there is only one, say, of these stations that get 0 as backoff, and that station would then win access to the channel and then send its frame. So it continues like this. There is a frame, there is a little bit of collisions here, which are resolved because the backoff time become more and more spread out, and eventually one of the stations become lucky, captures the channel, and all the other ones have to wait until the channel becomes available again. And then this process keeps on. So this is fairly typical, right? There is when you have random access, there is somebody who won the channel, then there is a little bit of fight for the channel, and there will be collisions, blah, blah, backoffs, and so forth. And then eventually somebody gets lucky and wins the channel, and keep on going like this. Questions? Okay. Then, if we then look at the Ethernet frame for the IEEE version of the Ethernet frame, it looks something like this. So again, we know that there is a payload, and the payload, when it's IEEE 802.3, we know that the upper layer is the LLC. Okay, that's the only upper layer in the 802 family. So we don't need to specify which protocol which is on top of 802.3 because we know it's going to be LLC. Okay, and then what else is there here? There is a preamble here, and that is for detecting that the frame is ongoing on the channel. So this is used by the physical layer to figure out, okay, there is a frame coming in. And then there is a byte here, which is called SFD, which stands for Start Frame Delimiter. Okay, so the preamble plus the start frame delimiter is 7 repetition of this sequence 10101010101010, right? And then the start frame delimiter is 10101011. Okay, so when the physical layer see there are two ones in succession, it knows that time is here. That now the frame starts in the sense that the next 6 bytes here is the destination address, and the next 6 bytes is the source address. So the destination and source addresses here, these are MAC addresses, and they are 48-bit long, each of them, right? 6 bytes is 48-bit. And then there is a length field, and the length field tells us how long, let's see, number of bytes in the payload, so in this one, because this could vary. The maximum length of this is 1500 bytes, so that's what Ethernet can handle. It has a maximum size of the payload, and this is fairly typical for protocols. They can few protocols can handle arbitrary lengths, right? Especially on the link layer, I don't know if any can do this. Okay, but you know also that there is a minimum frame length, because we need from here to here to be at least 64 bytes. Remember that was the minimum frame duration. So if this is very small, only a few bytes, then we need to add a few 0 bytes here to make sure that this field is at least 46 byte long. Okay. And then at the end there is 4 bytes of a CRC. Okay. And then if we count here, we have 6 plus 6 plus 2 plus 4, that's 10, 18 bytes. And we need everything to be 64. So the minimum we can have this field to be is 46 bytes. Now an LSE PDU can be maybe just 8 bytes long. Could be, right? So we had then in that case to pad here. Okay, again a little bit of ugly things, right? Because we need things to work in practice. Addresses here could be of 3 kinds: unicast, multicast, or broadcast. We need broadcast, if you remember, we need that for making ARP working, this address resolution protocol. It's also used for other purposes. And the broadcast address this is in hexadecimal, so it's the all one address. F is 111, 4 ones. Right? Length field here, number of bytes of the payload. 0 bits in the pad field, and the frame checksum is a 32-bit CRC. Okay, and it covers the whole frame from here to here. So there is no protection for the preamble, and it's not needed because it's always the same, right? And that's only used for the physical layer to synchronize. But all the important data here is protected by the frame CRC. Okay, and then again, as I said earlier, there is only one single upper layer, it's the LLC. So that in itself would then identify the upper layer protocols above LLC. But that's not the problem for 802.3. It only has one particular upper layer, the LLC. Questions? Okay, so then the problem now is that there are 2 Ethernet standards. One which is the 802.3, and the other one is this Ethernet version 2. So Ethernet 2 or standard Ethernet or DICS Ethernet. These are all the same. So it's a little bit problematic that if you look at the timeline, Ethernet 2 is actually an earlier than Ethernet in the 802.3 sense. Okay, so this is the early standard, even though it says Ethernet 2. Okay, there was an Ethernet 1 also, but 802.3 came after this. So how does it look? It looks exactly the same as the 802.3 frame, except for this field. Okay, so if we go back, we see that this is the length field in 802.3. In DICS Ethernet is the type field. And the type field here is used to identify the layer which is above Ethernet. Okay, so for DICS Ethernet, the upper layer could be is not LLC. It could be something else, or it supports many protocols. I guess it could be LLC, but it could be also other things. So the upper layer PDU here, which upper layer it is identified by this type field. Okay. So DICS, what does that stand for? It stands for Digital Equipment, Intel, and Xerox. So these were big companies at the time. I guess Intel is still a big one. Xerox is a little bit smaller. I don't know if Digital Equipment exists as its own company anymore. But anyways, these three companies got together and then specified Ethernet, this Ethernet. Type field is used to identify upper layer protocol. Type field starts at 0600 hex, hexadecimal. And this number is actually greater than a maximum value of the 802.3 field, which is 1500 in decimal, which is 05 DC. Okay, so why is this important? Well, if a network interface card captures an Ethernet frame and then looks at this 2 bytes and wants to know, is it a DICS2 frame or is it a 802.3 frame, it can actually learn this by just looking at these 2 bytes. If these 2 bytes here is less than 1500, it's an 802.3 frame. If these 2 bytes are larger than 1500, it's a DICS Ethernet frame. Okay. So both of these frames can exist on the medium at the same time, and the network interface card can just look at these 2 bytes and determine which frame version is it that I have at the moment here. An interesting thing here is that DICS Ethernet supports up to 1500 byte long packets. And why is that? Well, it's because the whole thing here can be allocated to the upper layer protocol, just as we did previously. But in 802.3, the upper layer is a LLC, which means that the upper layer to LLC cannot have a 1500 byte long packet. Okay, so let me try this again. DICS Ethernet supports up to 1500 byte long IP packets, right? Because this type could say it's IP above me, and the whole thing here could be an IP packet. For 802.3, it's not true, because then it can only support up to 1492 long IP packets, byte long IP packets. And why is this? Well, it's because LLC and Snap has an overhead of a total of 8 bytes. So if we go back, we see that the LLC overhead here is 8 bytes, and the IP packets needs to be put in here. And if this is limited to 1500 bytes, the IP packet cannot be more than 1492 bytes long. Okay. So this seems to be a minor difference, right? What difference is there between 1500 and 1492? Well, if you're really concerned about efficiency for IP, which one would you choose? Well, you would choose DICS Ethernet, right? Because you can have longer packets for IP in that case. So it turns out that most IP packet in practical networks is carried by these DICS Ethernet frames rather than 802.3. Okay, so this is I mean, if you wonder which one is most used today, if it's for IP packets, it would be Ethernet 2 or DICS frames. Okay, so what can we say more about the 802.3 physical layers then? Well, there is a bunch of them, and they have evolved over time. So at the beginning of time, now we're talking about late 70s, early 80s, I forgot, but in that time range. The first 802.3 standard specified 4 different physical layers. and it's this 10 base 5 and 10 base 2 and 10 base t and 10 base fx. So what does that mean? Well, first of all, the 5 here means that the maximum length of the cable is 500 meters. The 2 here means that the maximum length is 200. The T here means it's a twisted pair cable, and the FX means optical fiber. Okay. I don't know why this is done. It's kind of stupid, but that's how it is, right? This thing base here means that we are doing baseband transmissions. We're not doing QAM or anything like this. And the 10 here is because this is 10 megabit. Is it? I think so. Yeah, I think it's because of 10 megabits. We'll see on the next slide if this is true or not. I actually forgot. It's embarrassing. But anyways. So anyways, if we look at this was the first one. So it has some hosts, and then there is this coaxial cable. It's a rather thick coaxial cable. So it's kind of bulky and things like that. So it was stiff, a little bit hard to work with. So then one took a little bit thinner coaxial cable, and then in this standard here. And this one was a little bit better, but these connectors were kind of flaky. So neither of these are, there are no new deployments of this. So this is all historical stuff. So I'm sure there's some Ethernet somewhere that still has this, but most of it is already ripped out, so it's not used anymore. So the next standard that came, okay. So if we want to connect several LANs together with each other, or how do we do this? Well, there are two different ways we can connect LANs. They're either with hubs or switches. So if we have a hub, what does that mean? Well, it basically means that we connect all the cables to a particular device here, which logically is just a electrical connection together, right? So it basically, from a logical point of view, this just looks like another piece of cable. Okay, so this is a physical layer device or layer 1 device. It does not change, it doesn't inspect any link layer addresses or do any filtering of the packet that goes in here goes out here. So a packet that goes in here, it goes out here, it goes out here, and it goes out here, right? So this means that this is just an extension of the cable in a sense. Okay, but there is this star topology, right? You can draw, instead of sharing a cable and drilling holes in it, you take your cable from your host and you plug it into your hub. Right. Switch, on the other hand, is a layer 2 device. So this is a link layer device, a layer 2 device. So how does that work? Well, the packets that go into this, there's still cables connected to a box, but the packets that go in here are decoded, and link layer addresses are inspected and so forth. It's buffered in here, and then a packet that goes in here is then inspected, what is the destination address, and then it goes out on the LAN where the destination is. So it doesn't go out in the other branches here, as opposed to the hub here. Okay, so which one do you think is the best? Yeah, the switch, right? And the reason for this is that if we have, for the same amount of traffic here, the switch is able to isolate transmissions from going from destination to, from source to destination. So at the same time, we could have another packet going this way, and it can go at the same time without interfering with each other, right? So this is sometimes called that we isolate the collision domains. Because where can collision occurs here? Well, in the left-hand side here, collisions can occur at all these segments, while in the right-hand side, the collision can only occur on this segment and on this segment, right? So each of the cables here becomes then what's known as their own collision domain, where collisions can occur. And the fewer things which are attached to a collision domain, the less collisions we will have, right? And the better the performance will be. Okay, so for this reason, switches is the go-to thing, right? So we have these devices. So this is an Ethernet switch. So this is a layer 2 device. It's not a layer 1 device. So packets that goes in one port goes out in another port, and there could be multiple packets going in and out of this at the same time. Okay. Let me just finish off this, and we'll take 15 minutes when there is a good break here. So the next thing that happened in this was to go to fast Ethernet. So here I was right. Now it's 100 in front of it because it's 100 megabits per second. It's still T here for twisted pair. 4 means category 3. I don't know why it's called. Okay, so it has to be at least category 3. There is TX here, means at least category 5 cables. So this one happens to be, what is it? It doesn't say. I would guess it's a category 5 cable. Could be a 4 also, I don't know. But anyways, probably category 5. Pretty sure it's it, right? And then there was also a fiber option, and what is dominating is this thing here. Now, so to preserve compatibility with the 10 megabit Ethernet, we use the same frame format with the same interface, the same protocols. So nothing has changed here a little bit. However, we have reduced the segment length here. Why is that, do you think? So the segment length is the length of the median. Why do we have to do this? It's because we want the T slot to be larger than 2 T prop. If we keep this fixed, right, and this happens to be 64 bytes, which on 10 megabits per second was this 51.2 microseconds for 10 megabit per second. For 100 megabit per second, how much is 64 bytes then? Divide by 10, right? Okay, so it's 5.12 microseconds. But we still want this slot to be larger than 2 times the propagation time, otherwise things will break. So what do? Well, we change the propagation time by limiting the length of the segment. Right? You reduce the size of it, same propagation speed, so therefore lower propagation time. Okay, so that was the fix here. So what to do then when we go to gigabit, right? The same problem occurs, right? And now the choice was actually to increase the slot time in the sense that we increase the number of bytes required for this. Now you see that the slot time is 496 nanoseconds, which is essentially the slot time we had earlier also in 100 megabit per second Ethernet, right? But here, instead of reducing the segment length to very short, one increased the minimum frame length of the packets here instead. Okay, and then were a bunch of other things, and the most important thing here is that this CSMA CD was essentially abandoned. It's still in the standard, but now the structure is such that we always plug this into a switch, and if there is a switch between the computer and here, there is no need for a MAC for this one because it's full duplex. So on one direction here, there is only one transmitter, which is the laptop. On the other direction, it's only one transmitter, which is the switch. No need for medium access control, right? So why do carrier sensing? It's completely useless, right? It was still kept in the standard, but essentially it's never used, right? And then when 10 gigabits, then it was eventually officially abandoned, right? So there is no MAC scheme left here because it serves no purpose, actually. Okay, so I think I'll stop here. And so the key thing here is that Ethernet has been evolving during the years, and since it's an evolving standard, we have to patch it when we upgrade it a little bit to new requirements and also to new data rates and so forth. And there are various ways one can do that. But it's turned out to be a very, very successful set of standards. So this is the dominating LAN standard today. There are two types of frame formats, as we saw, the 802.3 frame and the DICS Ethernet frame. Both are used. Okay. So when one talks about Ethernet, it's not a single standard. It's a bunch of different variations along this theme. Okay, so let's take 15 minutes.